A monster lurks in the heart of our galaxy. It is a supermassive black hole, an invisible giant whose gravity holds everything together. These cosmic engines are not just destroyers but master architects, and they hide truths that challenge the very laws of physics. Over the next 50 secrets, you will journey from their violent birth to their ultimate, mind-bending fate. You will learn how they build galaxies, warp time, and might even be portals to other realities. How did these behemoths appear so soon after the Big Bang? What happens to the information they consume? By the end, you will see the universe in a completely new light. What single cosmic mystery do you hope will finally be solved? This silent presence at the center of our galaxy is not an anomaly. The first great secret is that nearly every large island of stars, from majestic spirals to glowing ellipticals, holds one of these supermassive giants in its heart. Think of it not as a random monster, but as the galaxy's underlying heartbeat, a gravitational anchor that was present from the very beginning. This relationship is far from coincidental. Astronomers have uncovered a stunning correlation, a cosmic rule that seems to govern the universe. The more massive the galaxy, the more massive its central black hole. A giant elliptical galaxy, for instance, will host a black hole billions of times heavier than our Sun, while a smaller spiral like our Milky Way has a comparatively modest one, weighing in at a few million solar masses. This tight relationship suggests a profound co-evolution, a dance that has lasted for billions of years. The galaxy and its black hole grew up together, each influencing the other's destiny. The black hole's gravity shapes the orbits of the innermost stars, while the galaxy itself provides the raw material for the black hole to consume and grow. They are locked in a gravitational embrace, two parts of a single, unified system. How did this partnership first begin? The answer lies in the chaotic dawn of the cosmos. But how do you measure something you cannot see? This is the second great secret, the art of weighing an invisible giant. Astronomers cannot simply put a supermassive black hole on a cosmic scale. Instead, they become celestial detectives, observing the effects of its overwhelming gravity on the world around it. One of the most powerful methods relies on watching the stars themselves, a technique called stellar dynamics. Picture a swarm of stars orbiting furiously around the galaxy's empty center. These are not gentle orbits, they are frantic, high-speed races. By measuring the velocities of these stars with incredible precision, scientists can calculate the mass of the unseen object they are dancing around. The faster the stars whip past, the more massive the hidden anchor must be. It is like deducing the size of a hidden magnet by watching how fast iron filings swirl around it. Another method observes the black hole's dinner plate, the glowing disk of superheated gas known as an accretion disk. This is gas dynamics. As material spirals inward, it moves at different speeds depending on the gravitational pull at the core. By mapping the motion and temperature of this glowing maelstrom, researchers can weigh the monster stirring the pot. Then there is the most direct observation yet, the monumental work of the Event Horizon Telescope. This is not a single telescope, but a global network of observatories working in unison to create an Earth-sized instrument. Its first historic image revealed the shadow of the black hole at the heart of Galaxy Messier 87, a dark silhouette against a backdrop of fiery light. This shadow is not the black hole itself, but the absence of light captured by its event horizon, the point of no return. It is a blurry picture, but a profound one, offering a direct glimpse of the invisible and confirming the staggering mass predicted by other methods. Each technique, from tracing stellar races to capturing a cosmic silhouette, confirms the same incredible truth. A gravitational behemoth weighing millions, even billions of suns is hiding in plain sight. These gravitational giants were already ancient when the universe itself was in its infancy. This is the third secret, the puzzle of the primordial seeds. Fully formed supermassive black holes with masses billions of times that of our Sun are seen shining from the cosmic dawn, a mere few 100 million years after the Big Bang. This presents a monumental challenge for cosmology. How could something so immense grow so incredibly fast? There simply was not enough time for them to form by any ordinary means we understand. The leading theory to solve this riddle is a process of staggering violence called direct collapse. Imagine a cloud of pristine primordial gas, a cloud of cosmic proportions. Under normal circumstances, such a cloud would fragment, cooling down to birth a multitude of stars. But in the dense, hot environment of the early universe, something different could happen. The gas could remain hot, refusing to splinter, and collapse under its own immense weight in one single catastrophic event. This would bypass the star formation stage entirely, creating a black hole seed tens of thousands, even 100,000 times more massive than our Sun right from the very beginning. This is not a star that died, it is a monster-born whole. Other theories suggest different paths. Perhaps the first generation of stars were true leviathans, supermassive stars hundreds of times heavier than anything we see today. These colossal blue giants would have lived fast and died young, collapsing directly into substantial black hole seeds after their brief, furious lives. Another possibility is a slower, more patient assembly through successive mergers. Smaller black holes, the remnants of the first stars, could have spiraled together, combining over and over in a dense stellar environment. Yet even this process seems too slow to account for the titans we observe so early. The existence of these ancient behemoths forces us to reconsider the very first chapters of cosmic history. What strange conditions in the infant universe allowed for such rapid, violent birth? The answer is written in the light of the most distant quasars, and we are only just beginning to learn how to read it. Not all supermassive black holes are created equal. Beyond their sheer mass, they possess a hidden dynamism, a spin that is a fossil record of their violent birth. This is the fourth secret, the spin of destiny. As a black hole forms, all the swirling, chaotic motion of the gas, stars, and smaller black holes it consumes gets funneled into a single, defining property, rotation. This spin is not a gentle turn. It can accelerate the very fabric of spacetime around it to velocities approaching the speed of light. The effect is so powerful it literally drags the universe along with it, a phenomenon known as frame dragging. Imagine spacetime as a vast, still sheet of fabric. A non-spinning black hole would be like a heavy weight creating a simple dip. But a spinning black hole is like that same weight set into a furious whirl, twisting the fabric around it into a cosmic whirlpool. Anything caught in this ergosphere, the region just outside the event horizon, is forced to move with the spin. It is a place where standing still is impossible. This incredible rotational energy does not stay locked away. It becomes the primary power source for the most dramatic structures in the universe, relativistic jets. These are colossal beams of radiation and matter shooting out from the black hole's poles for thousands of light years. The twisted magnetic fields, amplified by the spinning monster, act like a cosmic slingshot, channeling infalling material and hurling it back out into the void at nearly light speed. A black hole, the ultimate consumer, is also one of the universe's most powerful engines. Yet for all this ferocious activity, black holes are paradoxically the simplest objects in the cosmos. This brings us to the fifth secret, the cosmic no-hair theorem. It is a strange and profound idea with a peculiar name, suggesting that black holes have no hair, no distinguishing features. In practice, this means that every single detail about the material that falls in, every atomic structure, every chemical composition, every memory of a star or a planet, is utterly and irrevocably erased. The only properties that remain, the only things an outside observer could ever measure, are just three: mass, spin, and electric charge. A black hole made from 100 suns and a black hole made from 100 planets, provided they have the same mass, spin, and charge, would be completely identical. It is as if the universe has a fundamental forgetfulness. The incredible complexity of everything that crosses the event horizon is boiled down to 3 simple numbers. This theorem is a statement about information, and it poses one of the greatest paradoxes in modern physics. If information cannot be destroyed, where does it all go when it falls into a black hole? The answer to that question may lie in the quantum fuzz surrounding the event horizon itself, a secret we are only beginning to unravel. This boundary of no escape, the event horizon, is not a solid surface you could crash into. It is a mathematical point of no return, a one-way gate woven into the fabric of spacetime itself. Think of it as the edge of a cosmic waterfall. For a long time, you can swim against the current, fighting the pull of the water. But once you cross the precise point where the water's velocity exceeds your swimming speed, the struggle is over. You are going over the edge. The event horizon is that precipice for space-time, where the inward flow of space itself exceeds the speed of light. Nothing, not even light, can swim upstream fast enough to escape. This leads to a crucial clarification. Black holes are not the cosmic vacuum cleaners of popular fiction, endlessly sucking in everything from vast distances. Their gravity is powerful, but it is still gravity governed by the same rules as our sun's. If you were to replace our sun with a black hole of exactly the same mass, the Earth and all the other planets would continue orbiting in their exact same paths, plunged into permanent night but not pulled inward. The danger zone is only when you venture incredibly close, crossing that invisible threshold where the laws of physics as we know them break down. So what does happen to the unlucky matter that crosses this ultimate boundary? Theoretical physics paints a strange and violent picture. From the perspective of an outside observer, time for the infalling object would appear to slow to a complete stop at the event horizon, its image frozen and red shifted into oblivion. But for the object itself, the journey continues. It would be stretched into a stream of atoms by immense tidal forces, a process whimsically called spaghettification, before presumably being crushed into the singularity at the very center, a point of infinite density where all our known laws of physics cease to have any meaning. And with that destruction comes the great information paradox. All the unique data that define that object, from its atomic structure to its history, seems to be permanently erased from our universe, violating a fundamental tenet of quantum mechanics. The event horizon is not just a physical boundary, but a cliff edge for reality itself. Crossing the event horizon is only the beginning of the nightmare. The 7th secret reveals the grotesque fate of any matter that strays too close, a process known as spaghettification. This is not a gentle stretching. It is the ultimate demonstration of tidal forces, the same kind of gravitational pull that the moon exerts on Earth's oceans, amplified to a lethal cosmic extreme. The key is the difference in gravity's pull across an object. Your feet, being closer to the black hole, would feel a vastly stronger gravitational pull than your head. The result is a violent, simultaneous stretching and compression. You would be pulled vertically into a long, thin stream of atoms while being squeezed horizontally from all sides. A star venturing too close would be transformed from a sphere into a luminous noodle of superheated plasma, spiraling into the darkness. This is the universe's most brutal and fundamental reshaping, reducing complex structures to their most elementary form. But even this stream of particles has a final destination. It is drawn toward the 8th and most profound secret, the paradoxical heart of the black hole itself, the singularity. This is not a physical object you could touch. According to Einstein's theory of general relativity, it is a single, infinitesimal point where all the black hole's mass is crushed into zero volume. The density and the curvature of spacetime become infinite. Our mathematical models simply break down. The rules that govern planets, stars, and galaxies cease to apply. Here at the singularity, the two great pillars of modern physics, general relativity and quantum mechanics, collide in a fundamental conflict. General relativity, which describes gravity as the curvature of spacetime, predicts this infinite point with unwavering certainty. Yet quantum mechanics, which governs the bizarre world of the very small, insists that such a singularity is impossible. In the quantum realm, there are no perfectly defined points or certainties, only probabilities and fields. The idea of infinite density violates the core quantum principle that information cannot be destroyed. This is more than a theoretical disagreement. It is a battle for the soul of physics, a screaming paradox hidden at the center of the darkest objects in existence. The singularity represents a frontier where our current understanding ends, and a deeper, more complete theory of quantum gravity must begin. This fiery ballet of matter is the black hole's most visible signature, a swirling vortex of doom known as the accretion disk. It is not a peaceful, orderly orbit like the rings of Saturn. This is a chaotic, superheated maelstrom where gas, dust, and even entire stars are torn apart into a glowing plasma. As this material spirals inward, drawn by the black hole's immense gravity, it does not fall straight in. Instead, it piles up into a flattened, rotating disk, much like water circling a drain. The particles within this disk rub against each other with tremendous violence, creating immense friction. This friction, combined with the crushing gravitational forces, heats the material to temperatures of millions of degrees. At such extremes, the disk does not just glow with visible light. It radiates brilliantly across the entire electromagnetic spectrum, from radio waves to incredibly energetic X-rays. This is why we can see these invisible monsters at all. Their dining tables are set with a feast of light. The properties of this light are a treasure trove of information for astronomers. By analyzing the disk's temperature and its total luminosity, its sheer brightness, scientists can deduce the black hole's feeding habits and even weigh the hidden giant itself. A hotter, more luminous disk typically indicates a black hole that is feasting voraciously on a large amount of material. A quieter, cooler disk suggests a period of fasting. The very size and structure of the disk can also reveal the black hole's spin, as a rapidly rotating black hole can warp the inner regions of this fiery ring. This glowing whirlpool is more than just a light source. It is the black hole's voice broadcasting its secrets across the cosmos, and sometimes that voice becomes a deafening scream, a phenomenon tied to the next great secret, the mysterious quasars that outshine entire galaxies. That fiery accretion disk can become a beacon so intense it outshines the galaxy that hosts it. These are quasars, the 10th secret, the most persistently luminous objects in the entire cosmos. A single quasar from a region not much larger than our solar system can blaze with the light of 1 trillion suns, outshining every single star in its home galaxy combined. This incredible power does not come from nuclear fusion like in stars, but from gravitational fury. A quasar is simply a supermassive black hole in its most voracious, gluttonous phase, gorging on a staggering amount of gas, dust, and stars. Its accretion disk becomes a superheated, radiant maelstrom, converting the gravitational energy of infalling matter into a flood of radiation with unbelievable efficiency. This is a black hole at the peak of its power, a cosmic engine running at full throttle. Because light takes time to travel across the vast universe, when we observe these brilliant beacons, we are not seeing them as they are now. We are looking directly into the past. The most distant quasars appear to us as they were when the universe was young, just a few 100 million years old. They are the hyperactive cores of infant galaxies in the process of formation. By studying their light, astronomers can peer back to an epoch when galaxies were first being assembled, their central black holes growing rapidly and violently. The sheer existence of these brilliant objects so early in cosmic history tells us that supermassive black holes were not a late addition to galaxies. They were there from the very beginning, shaping the growth of their stellar homes from the inside out. The quasar phase, however, is a temporary blaze of glory. As a galaxy ages and its central black hole consumes the available fuel, this brilliant beacon eventually dims, leaving behind the quiet, dormant giants we see in galaxies like our own Milky Way. So every quasar is a flash from the universe's youth, a brief, brilliant shout from a time of cosmic construction now silent. The incredible power of a feeding black hole does not just radiate outward as light. It can also be focused into two colossal, high-speed beams known as relativistic jets. These are not gentle streams, but narrow torrents of radiation and superheated plasma, ejected from the black hole's poles at nearly the speed of light. They can stretch for thousands, even millions of light years, punching straight through their host galaxies and far out into the intergalactic void. Their formation is a direct result of the black hole's spin and its powerful magnetic fields. As the accretion disk spins, it winds the magnetic field lines into a tightly coiled, twisted funnel, channeling material away from the poles. This cosmic slingshot, powered by the black hole's own rotational energy, accelerates the infalling matter and hurls it back out into space in a stunning display of raw power. This entire process reveals the black hole's true nature as a gravitational battery. Think of a hydroelectric dam. Water at the top of the dam holds a huge amount of gravitational potential energy. As it falls, that energy is converted into electricity. A black hole operates on the same fundamental principle, but on a cosmic scale. The matter spiraling in the accretion disk is like that falling water. It possesses immense gravitational potential energy simply by virtue of its position deep within the black hole's gravitational well. As it falls inward, that stored energy is not lost. It is converted with breathtaking efficiency into other forms. Friction and collisions within the disk transform it into the intense heat and light we observe. The magnetic slingshot converts it into the kinetic energy of the relativistic jets, propelling matter across the universe. A single black hole can convert matter into energy with up to 40% efficiency, far surpassing the paltry 0.7% efficiency of nuclear fusion that powers stars. This is why a quasar can outshine a trillion suns. The black hole is not just a consumer, it is the universe's most powerful and efficient battery, taking the gravitational promise of matter and unleashing it as a cosmic firestorm. That spinning black hole we just described is not the only kind. The 13th secret reveals a fundamental division in the family of black holes, a choice between a simple sphere and a cosmic whirlpool. On one hand, we have the Schwarzschild black hole, the simplest model possible. It is a black hole with mass but no electric charge and, most importantly, no spin. Picture a perfect, featureless sphere. Its event horizon is a simple boundary, a one-way surface shrouding the singularity at its center. This is a black hole in its most basic, almost theoretical form. In reality, almost every black hole in the universe is born from a collapsing, rotating system, inheriting that spin and becoming a Kerr black hole. This is where the simplicity ends and the true complexity begins. A Kerr black hole is not a perfect sphere. Its rotation flattens it at the poles and bulges it at the equator, much like our own spinning Earth. This distortion creates a region of twisted spacetime just outside the event horizon, the ergosphere. In this region, spacetime itself is dragged along with the black hole's rotation, forced to move in the direction of the spin. Nothing can remain stationary here. It is a cosmic riptide where standing still is a physical impossibility. This critical distinction makes all the difference. A simple Schwarzschild black hole is a quiet end. But a spinning Kerr black hole is a dynamic engine. Its rotational energy can be tapped, its twisted magnetic fields can power relativistic jets, and its ergosphere could, in theory, be a source of immense power. This is why astronomers are confident that the supermassive giants at the hearts of galaxies are almost all black holes. They are not simple spheres of darkness. They are furious, spinning maelstroms, their rotation a permanent record of everything they have ever consumed. Even a perfect vacuum is not truly empty. At the tiniest scales, space itself is a seething sea of activity, a quantum foam where pairs of virtual particles constantly flicker in and out of existence. Usually, these particle pairs, one of matter and one of antimatter, annihilate each other almost instantly, returning their borrowed energy to the universe. But near the event horizon of a black hole, something extraordinary can happen. If this quantum flicker occurs right at the precipice, one particle can fall across the boundary of no return, while its partner escapes into the cosmos. The particle that escapes carries away a tiny amount of energy, and to conserve the universe's energy budget, the black hole itself must lose a corresponding amount of mass. This is Hawking radiation, a slow, quantum mechanical leak from the most gravitationally powerful objects in existence. For a supermassive black hole, this effect is utterly negligible. The trickle of escaping particles is vastly overshadowed by the cosmic microwave background radiation it absorbs. It would take an almost unimaginable length of time, far longer than the current age of the universe, for a giant black hole to lose any significant mass through this process. But for a hypothetical tiny, primordial black hole, perhaps the size of an atom but with the mass of a mountain, Hawking radiation would be a roaring torrent. Such a tiny object would have a much stronger gravitational gradient at its event horizon, amplifying the quantum effect. It would radiate away its mass furiously, growing hotter and brighter until it presumably vanishes in a final, explosive flash of gamma rays. The profound implication of Hawking's work is that black holes are not eternal. They have a life cycle and they can die. This slow evaporation creates the black hole information paradox in its most acute form. If a black hole evaporates completely, what happens to all the information about the stars and gas that fell into it? Is it truly lost forever, or is it somehow encoded in the Hawking radiation itself? This quantum whisper is our first real clue that the answers to the universe's biggest mysteries lie where gravity meets the quantum world. The quantum whisper of Hawking radiation introduces a deep and troubling conflict, the information paradox. This is one of the greatest puzzles in all of physics, a direct clash between our two most successful theories of reality. On one hand, quantum mechanics, the rulebook for the subatomic world, states with absolute certainty that information cannot be destroyed. Every particle, every atom carries a unique identity, a set of quantum properties that define it. This information can be scrambled, mixed, and transformed, but it must always, in principle, be recoverable. It is a fundamental law of the universe, like saying you can always unscramble an egg if you have perfect knowledge. On the other hand, general relativity, which describes gravity and black holes, seems to demand that information is permanently erased. When matter crosses the event horizon, it is crushed into the singularity, and all the details that made it a star, a planet, or a person are lost forever. The black hole only remembers the total mass, spin, and charge. This creates an impossible situation. How can both of these foundational theories be correct if they give completely different answers to the same simple question: what happens to the information? One radical proposal to solve this is the firewall paradox. It suggests that the event horizon is not a peaceful, empty space as Einstein's equations describe. Instead, it could be a searing wall of high energy, a literal firewall that instantly incinerates anything trying to cross. This firewall would preserve quantum information by destroying the infalling object before it could pass the point of no return, but it completely violates the principle of equivalence, a cornerstone of general relativity which states that someone in freefall should not feel any dramatic local effects at the event horizon. You cannot have both a smooth spacetime and a fiery death wall. So where does the information go if it is not destroyed? Modern theories propose some mind-bending solutions. One idea is that the information is never actually lost inside the black hole. Instead, it is stored in a scrambled, two-dimensional form on the event horizon itself, like a cosmic hologram. The three-dimensional information about everything that falls in is encoded on the two-dimensional surface of the horizon. Another possibility is that the information is not lost at all, but is slowly and chaotically leaked back out into the universe, encoded in the very Hawking radiation that the black hole emits. The radiation would not be random, but would carry a faint, impossibly complex imprint of everything the black hole ever consumed. The paradox forces us to confront the limits of our knowledge, hinting that a deeper theory of quantum gravity must exist, one where spacetime itself has a quantum structure and information is always preserved, even in the darkest of places. A star's final moments can be a brilliant flash of cosmic violence. When one wanders too close to a supermassive black hole, it experiences a tidal disruption event. The star is not swallowed whole. Instead, the immense difference in gravity between the side closest to the black hole and the side farthest away stretches it horizontally while compressing it vertically. This tidal force overcomes the star's own gravity, pulling it apart into a long, thin stream of superheated gas. About half of this stellar debris is flung out into the void, while the rest swings back around, forming a temporary, intensely bright accretion disk. For a few months, this flare can outshine every star in its galaxy, a final, fiery testament to a star that ventured too close. This is the black hole's most dramatic meal, a single, catastrophic feast after perhaps millions of years of fasting. This leads directly to the black hole's unpredictable diet. These giants are not constant consumers. They lurk in the dark for eons, dormant and quiet, until a new source of fuel arrives. Their feeding cycles are dictated entirely by their environment. In a crowded galactic core, a close stellar encounter or the disruption of a gas cloud can send matter spiraling inward, triggering a period of activity. The black hole awakens, its accretion disk igniting into a brilliant ring of light, perhaps even powering jets. But once that specific meal is consumed, the feast is over. The black hole returns to its quiescent state, a silent giant waiting for the next cosmic accident to deliver its dinner. This cycle of binge and fast explains why some galaxies have brilliant quasars at their hearts while others, like our own Milky Way, harbor only a quiet shadow. It is a diet of chance and chaos, a reminder that even the most powerful forces in the universe are at the mercy of their surroundings. This violent cycle of feasting and fasting has a profound purpose. The 18th secret reveals that a supermassive black hole is not just a resident of its galaxy, it is the master regulator of its growth. This process, known as galactic feedback, creates a cosmic balancing act of breathtaking scale. When a black hole enters an active phase, gorging on gas and shining as a quasar, it does more than just blaze with light. The intense radiation and the powerful relativistic jets pouring from its poles flood the surrounding galactic core with immense energy. This energy heats the vast clouds of cold gas, the very raw material needed to form new stars, preventing the gas from cooling and collapsing. In more extreme cases, the black hole's winds can blow this star-forming gas completely out of the galaxy, stripping it clean. The galaxy's primary nursery is shut down. This is why the black hole's mass is so perfectly tied to the mass of the galaxy's central bulge of stars. The black hole grows until its own energy output becomes strong enough to shut off its own food supply. It is a self-regulating system, a cosmic thermostat. A galaxy cannot grow too large because its central engine will eventually switch on and halt the process. This feedback loop solves a long-standing mystery in astronomy. Without it, computer simulations show that galaxies would continue forming stars, growing into monstrous, star-rich behemoths far larger than any we actually observe. The black hole, in its most violent outbursts, is actually imposing order, ensuring its home galaxy grows in a stable, controlled manner. The most destructive force in the galaxy is, paradoxically, the very thing that gives it its final, stable shape. This precise cosmic rule is known as the M-sigma relation. It is one of the most astonishing correlations in all of astronomy. The mass of a galaxy's central bulge of stars is perfectly proportional to the mass of its supermassive black hole. A larger bulge always hosts a heavier black hole with a precision that seems almost too perfect to be a coincidence. The scale of this partnership is what makes it so difficult to comprehend. The black hole itself is an almost infinitesimal speck at the galaxy's heart, 1 billion times smaller than the vast stellar city it inhabits. Yet its mass is locked in a perfect dance with the billions of stars swirling around it. How can something so small be so perfectly connected to something so immense? This is the central mystery of the M-sigma relation. It implies that the growth of the black hole and the growth of the galaxy are not separate events. They are two sides of the same cosmic coin, an intimate connection spanning billions of years. But which one leads the dance? Does the galaxy build the black hole, or does the black hole build the galaxy? This question sparks a fierce and ongoing debate among astronomers. One compelling theory gives the black hole a dominant role. In this scenario, the black hole acts as the ultimate galactic regulator. As it feeds and becomes more massive, its energetic outbursts, its quasars and jets, inject vast amounts of energy back into the galaxy. This feedback, as we learned, heats or blows away the gas needed to form new stars, effectively putting a brake on the growth of the central bulge. The black hole grows until its own power becomes strong enough to shut off its own fuel supply, and by extension, the growth of the bulge. It is a self-correcting system that naturally results in the tight correlation we observe. The black hole is the master and the galaxy is its domain. The other leading idea suggests a more equal partnership, a story of shared growth from the very beginning. In this view, the black hole and the galaxy grow in lockstep, both feeding from the same vast reservoir of cold gas flowing into the galactic center. Major galactic events like mergers with other galaxies funnel enormous amounts of this gas inward simultaneously, triggering a burst of new star formation for the bulge and a feast for the central black hole. They grow together because they are eating from the same cosmic table, their fates entwined from birth by the same external forces. The truth may lie in a complex combination of both processes, a delicate interplay where the black hole and its galaxy shape each other across cosmic time. This single, clean mathematical relation hides an epic story of construction and control, a billion-year tango between a speck of darkness and an ocean of light. Light itself is not immune to the pull of a supermassive black hole. The 20th secret is gravitational lensing, a phenomenon where the black hole's gravity acts as a cosmic magnifying glass, warping the very fabric of space so profoundly that it distorts the path of light from stars and galaxies lying far behind it. From our viewpoint, this creates a strange and beautiful distortion. A single background star might appear as multiple smeared images arranged in a perfect circle, an Einstein ring around the invisible dark giant. This lensing effect is not just a visual curiosity, it is a powerful tool. By measuring the amount of distortion, astronomers can directly weigh the black hole, confirming its mass independently of the stars whirling around it. It is nature's own scale, using the bending of light itself to measure the invisible. This cosmic trick of the light was pushed to its absolute limit with the Event Horizon Telescope's quest to capture the uncapturable. The 21st secret is the black hole shadow, a monumental achievement in human observation. The target was the supermassive black hole at the heart of galaxy Messier 87, a behemoth weighing 6.5 billion times more than our Sun. The resulting image, a blurry orange donut of light, is not the black hole itself. That is impossible. What you are seeing is the black hole's shadow, a dark central void silhouetted against the brilliant glow of its superheated accretion disk. This shadow is larger than the event horizon itself, a dramatic effect of extreme gravitational lensing. The light from the far side of the accretion disk is bent so violently over the top of the black hole that it reaches our telescopes, creating a ring of light that encircles the central darkness. The shadow is the closest we can ever come to taking a picture of the point of no return. It is the ghostly imprint of the event horizon, a confirmation of Einstein's theories on a scale he could only have dreamed of. That single, hazy image represents the collective effort of a planet-sized telescope, peering across 55 million light-years to see the shadow of a monster. Far from the galactic center, in the quiet outskirts of a spiral arm, another kind of monster can sometimes be found. These are the ultraluminous X-ray sources, objects that pour out staggering amounts of high-energy radiation, rivaling the output of an entire supermassive black hole's feast. Their very existence is a deep puzzle. How can something outside the core, where only stellar mass black holes should reside, shine with such ferocious intensity? The leading theory points to a missing link in the cosmic family tree, an intermediate mass black hole. Imagine a black hole that is neither the remnant of a single dead star nor a supermassive titan. This would be an object with the mass of hundreds, even thousands of suns, a true middleweight champion. Such a black hole, if it were accreting matter, could easily produce the incredible X-ray luminosity we observe, bridging the vast gap between the two known classes. Finding these intermediate black holes would complete our picture of how the supermassive giants first grew from humble seeds. But there is another, equally compelling possibility. What if these are not special black holes at all, but ordinary stellar mass black holes eating in an extraordinary way? This scenario involves a concept known as super-Eddington accretion. Every black hole has a theoretical limit to how brightly it can shine, called the Eddington limit. This is the point where the outward pressure from its own radiation pushes back against the inward flow of gas, creating a balance. But if matter falls in at a rate far beyond this limit, the rules change. The radiation can be trapped and absorbed, unable to escape to push back, allowing the black hole to gorge itself and shine with a brilliance that seems to defy physics. It would be like a tiny candle suddenly blazing with the light of a forest fire, its flame so dense and concentrated that it contains its own fury. So which is it, a missing middleweight or a gluttonous lightweight? The answer is that both could be true. Some of these brilliant X-ray beacons are likely one, and some the other. Their mystery forces us to admit that our simple classification of black holes is still a work in progress. The cosmos is filled with outliers and exceptions, reminding us that for every rule we write, the universe has a way of adding a fascinating footnote. The empty space around a galaxy is not truly empty. It is filled with an invisible presence, a ghostly substance we call dark matter. This mysterious material, which does not emit or absorb light, holds galaxies together with its gravitational pull. The 23rd secret asks a profound question. What is the relationship between this dark matter and the supermassive black hole at the galaxy's glowing heart? Could dark matter itself have been the catalyst for these cosmic giants? One compelling speculation is that in the early universe, dense knots of dark matter could have acted as the primordial seeds. These invisible clumps would have provided a gravitational anchor, pulling in vast amounts of normal gas far more efficiently than anything else. This rapid accumulation could have led directly to the formation of those impossibly massive black holes we see in the infant cosmos, solving the riddle of how they grew so big so fast. It is a theory where the unseen creates the unseeable, but the connection might be more indirect. Dark matter forms an immense, diffuse halo that envelops the entire galaxy, dictating its overall structure and gravitational potential. The shape and density of this dark matter scaffold guide how gas flows into the galactic center over billions of years. In this scenario, dark matter does not build the black hole directly, but it controls the faucet, regulating the flow of fuel that the black hole consumes. It is the ultimate puppet master, shaping the galaxy in the dark and, in doing so, governing the growth and activity of the monster at its center. The profound challenge is that dark matter remains one of the universe's greatest enigmas. We can see its gravitational effects, but we do not know what it is made of. This means that any link to black holes is, for now, a fascinating speculation built upon a fundamental mystery. It is a cosmic detective story where we are still searching for the primary suspect, a reminder that the darkest secrets of the universe are often hidden in plain sight. Galactic collisions are the most violent events since the Big Bang, and when two galaxies merge, their central black holes are destined for a gravitational dance. These giants, each weighing millions or billions of suns, sink toward the new common center through a process called dynamical friction. They push stars and dark matter out of their way, losing energy and spiraling ever closer until they are locked in a tight orbital embrace. This is a binary supermassive black hole, two invisible titans circling one another, their gravitational field whipping the surrounding stars into a frenzied orbit. Such a pair should be the ultimate source of gravitational waves, ripples in spacetime predicted by Einstein. Yet for a long time, these binary systems were purely theoretical. The final stage of their cosmic dance presents an immense puzzle known as the final parsec problem. Once the black holes get within about 3.2 light-years of each other, the mathematics of general relativity hits a wall. At this distance, they have effectively cleared out their immediate neighborhood. There are not enough stars or gas clouds left to rob them of more orbital energy through dynamical friction. They enter a cosmic stalemate, forever circling each other across that last critical parsec, unable to get close enough for gravitational waves to take over and seal their fate. This is a major headache for astrophysics because if black holes cannot merge, our models of galaxy evolution are missing a crucial piece. How do they finally bridge that gap? The solution may lie in a third actor, a massive gas disk that can form in the merged galactic core. This swirling reservoir of material can act as a gravitational brake, absorbing the black hole's momentum and drawing them relentlessly inward. Or perhaps a third supermassive black hole from a previous triple merger could kick the binary into a tighter orbit. The universe seems to find a way to solve its own puzzles, forcing these dark giants together in a final, universe-shaking collision. When that final cosmic stalemate is broken, the resulting merger unleashes a violence that literally reshapes the universe. The collision of two supermassive black holes is the most powerful event since the Big Bang itself. This is not an explosion of light or matter, but a shudder in the very fabric of reality, a gravitational wave. Imagine dropping a stone into a still pond. The ripples spread outward, warping the surface of the water. A black hole merger does the same thing to spacetime. The final, frantic orbits of the two giants whip spacetime into a frenzy, sending out waves of distortion that travel across the cosmos at the speed of light. These are not the high-frequency chirps detected from stellar mass black holes. The waves from supermassive mergers are deep, low-frequency rumbles with wavelengths so long they can take years to oscillate. A single wave from such an event might be larger than our entire solar system. We have not heard them yet because our current observatories on Earth are not built to listen for these cosmic bass notes. Our planet is too noisy, its seismic rumbles and human activity drowning out this profound, universal hum. But a new era of listening is on the horizon. The Laser Interferometer Space Antenna, or LISA, is a future space-based observatory designed specifically to hear this silent symphony. It will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. As a gravitational wave passes through, it will ever so slightly stretch and squeeze the space between the satellites, LISA lasers will detect these minute changes, a distortion smaller than the width of an atom across a vast distance. This will open an entirely new window into the cosmos, one based not on light but on gravity itself. Through this window, we will hear the history of galaxy assembly. Every major merger throughout cosmic time, every pairing of dark giants, has left its imprint in this background sea of gravitational waves. LISA will listen to this fossil record, tracing the growth of galaxies by the echoes of their colliding hearts. It will tell us how often these mergers happened, how massive the black holes were, and finally solve the mystery of how they overcome that final parsec. We are on the verge of hearing the universe's deepest, most fundamental vibrations, the aftershocks of creation itself. That final, violent merger can sometimes fire a supermassive black hole clear out of its own galaxy. This is the incredible recoil, a cosmic kick born from the most asymmetric of collisions. When two black holes spiral together, they radiate their energy away as gravitational waves. If the two giants are perfectly matched in mass and spin, these waves are emitted symmetrically, and the newly formed black hole sits peacefully at the center. But nature is rarely so tidy. If there is any significant imbalance, the gravitational waves carry away momentum in one preferred direction. To conserve momentum, the final black hole is kicked in the opposite direction, like a rocket firing its engine in reverse. The resulting velocity can be staggering, thousands of kilometers per second, a speed so great it can easily exceed the galaxy's own escape velocity. In a single, universe-shaking moment, the galaxy loses its heart. What remains is a wandering supermassive black hole, a rogue giant drifting in the profound darkness of intergalactic space. It travels without a home, without stars to govern, and without a glowing accretion disk to mark its presence. It is a true ghost, invisible and silent, its immense gravity detectable only if it chances to warp the light of a more distant galaxy, or if it begins to feast on a stray cloud of gas in the void. The existence of these cosmic loners solves another mystery. Why do some small galaxies appear to have no central black hole at all? Perhaps they once did, but a violent merger in their past sent their central engine flying into the abyss. The galaxy, robbed of its gravitational anchor, is left to evolve in a new and unpredictable way. This recoil is a reminder that even the most established powers in the cosmos are not immune to being overthrown by the fundamental laws of physics. Our own galactic center holds a secret written across the sky, stretching 25,000 light-years above and below the Milky Way's plane are two colossal spheres of energy, the Fermi bubbles. These are not made of stars or gas, but of incredibly high-energy gamma rays, a ghostly imprint of a long-forgotten cataclysm. They are the fossil remains of our supermassive black hole's last great outburst. Sagittarius, a star which today is a quiet and faint radio source, was once a brilliant and violent engine. Millions of years ago, it likely unleashed a titanic jet or a powerful spherical outflow, a blast of energy that punched straight through the galaxy's gaseous halo. This event would have been brief in cosmic terms, perhaps lasting only a few tens of thousands of years, but its effects are still visible today. The bubbles are the lingering echo of that explosion, their gas still glowing with the aftermath of that immense shockwave. This discovery fundamentally changes our understanding of our home galaxy. We do not live in a perfectly peaceful spiral. Our cosmic neighborhood bears the scars of a dramatic past, a time when the sleeping giant at the center awoke and roared, shaping the very space that surrounds our solar system. Our galaxy's core is a cosmic menagerie of the strange and unexplained. Among the stars whipping around Sagittarius, a star, astronomers have found bizarre entities known as G-objects. They look like puffy, extended clouds of gas, but they move like compact, massive stars. For years, their true nature was a complete enigma. How could a wispy gas cloud survive on such a tight, punishing orbit around a supermassive black hole? The tidal forces should have shredded it to pieces long ago. The leading theory is that a G object is actually a star in disguise, a stellar core that has been cloaked in a thick, obscuring shroud of gas and dust. This could be the result of a slow-motion stellar merger, where two stars spiraled together and merged, throwing off an immense envelope of material that now hides the single, more massive star at its center. Another possibility is that it is a single, bloated giant star that is having its outer layers gradually stripped away by the black hole's gravity, creating a trailing wake of gas that makes it appear as a cloud. These G objects follow orbits that bring them breathtakingly close to the point of no return, and with each perilous passage, a little more of their gaseous veil may be stripped away, revealing the dense stellar heart within. They are cosmic chameleons, and their dance with destruction helps us understand the extreme forces at work in the galactic center. This stellar oddity is paired with another, more ominous absence. The region immediately surrounding Sagittarius, a star, is suspiciously devoid of a certain type of star, the large, luminous red giants. Based on the normal stellar population of the galaxy, there should be many of these aging, expanded stars there. But they are missing. Their absence is a profound clue. One explanation is as violent as it is direct. A red giant is a star that has puffed up to a colossal size, its outer layers held by a relatively weak gravitational grip. When such a star wanders too close to the supermassive black hole, those tenuous outer layers can be easily ripped away by tidal forces in a process called tidal stripping. The star is robbed of its envelope, leaving behind only its exposed helium-burning core, which would appear much fainter and hotter, effectively disguising it from surveys looking for red giants. The other possibility is that the environment itself is too rough for these fragile giants to survive. The galactic center is a densely packed and chaotic place. Frequent, high-speed collisions between stars could literally knock the puffy atmospheres off red giants before the black hole itself even gets a chance to consume them. The core of our galaxy, it seems, is a place where stars are unmasked, stripped bare, and ultimately transformed by the relentless presence of the dark giant they orbit. Our own galactic giant is a study in cosmic restraint. Sagittarius, a star with a mass of 4 million suns, should be a brilliant beacon, yet it flickers with the faintness of a candle compared to the theoretical inferno it could produce. This is the 31st secret, the unusual quiet of a sleeping monster. The reason lies in the strange nature of its diet. Unlike the dense, rich feast that powers a brilliant quasar, the gas flowing toward Sagittarius, a star, is sparse, hot, and tenuous. It is a thin, meager soup rather than a steady river of fuel. In this state, the accretion process becomes radiatively inefficient. Most of the gravitational energy stored in the infalling gas is not converted into the intense heat and light of a glowing disk. Instead, the gas simply carries that energy with it, swallowing it whole across the event horizon. It is the difference between a roaring log fire and a single piece of charcoal dropped into a deep well. One releases a blaze of energy while the other just vanishes into the darkness with a faint hiss. This inefficiency is compounded by the black hole's current phase. It appears to be in a prolonged period of fasting. The chaotic stellar wins from the few dozen massive stars orbiting near by provide just enough sustenance to create a faint, flickering glow, but not enough to wake the beast fully. It is a giant nibbling on cosmic crumbs, its true power dormant, waiting for a larger meal to arrive. This quiet state is likely the norm for most supermassive black holes in the modern universe, a long, silent hibernation between the brilliant feasts of their youth. That crushing singularity at the center of a black hole might not be the final destination. A mind-bending possibility suggests that the very fabric of spacetime, warped to its absolute extreme, could tear open a bridge to another place or time. This is the speculative secret of wormholes, hypothetical tunnels through the folded canvas of the universe. In theory, The intense gravitational well of a black hole could be one mouth of such a tunnel, with the other end opening somewhere else entirely, another point in our cosmos, a different moment in history, or even a separate universe altogether. It is a shortcut on a cosmic scale, a concept that has fueled science fiction for generations. Yet the leap from fiction to physical reality is fraught with immense, perhaps insurmountable challenges. The primary obstacle is stability. A wormhole born from a black hole's singularity would be incredibly fragile, predicted to collapse into a pinprick in an instant, crushing anything inside before it could complete the journey. To keep this space-time tunnel open and traversable, you would need a truly bizarre substance to line its throat, something known as exotic matter. This is not just strange material from another world, but something that defies the known laws of physics. Exotic matter would need to possess negative energy density, creating a kind of gravitational repulsion that pushes the walls of the wormhole apart, preventing its immediate collapse. While quantum mechanics allows for fleeting regions of negative energy in a vacuum, the amount needed to stabilize a wormhole large enough for even a single atom is astronomical and far beyond any known or projected technology. This is why wormholes remain one of the most thrilling ideas in theoretical physics, a glorious mathematical possibility etched into Einstein's equations, yet they stand firmly in the realm of speculation. They are a beautiful reminder that our understanding of reality is incomplete, and that the darkest objects in the sky might one day be revealed as gateways to wonders we can scarcely imagine. If a black hole is a place where nothing can escape, its theoretical opposite would be a place where nothing can enter. This is the white hole hypothesis, a region of spacetime that violently expels matter and energy but allows nothing to cross its boundary from the outside. It is a one-way door swinging out into the cosmos, a cosmic fountain of endless creation. The equations of general relativity, which so perfectly describe black holes, are beautifully symmetrical, and they allow for such an object to exist in theory. This mathematical elegance leads to a profound and almost poetic idea. Could the Big Bang itself be the ultimate white hole, a singular event where the entire universe erupted from a point of infinite density, an outburst from which nothing could ever enter, only emerge? In this view, our entire cosmos is the expanding aftermath of a primordial white hole. Another tantalizing thought connects these two extremes. If you were to fall into a black hole, some speculative solutions to the equations suggest you might not end at a crushing singularity. Instead, your path could be funneled through a wormhole, a bridge in space-time, and you would be violently ejected out of a white hole in a completely different region of the universe, or perhaps even a different universe altogether. It paints a picture of black holes not as final graves, but as portals in a vast cosmic network. Yet for all its mathematical allure, the white hole remains a phantom. No astronomical observation has ever detected an object that behaves in this way. The universe seems to have a strong preference for one-way doors that pull matter in, not push it out. White holes are thought to be incredibly unstable if they could form at all, likely collapsing instantly under the weight of their own reality. So while they offer a breathtaking glimpse into the symmetry woven into the fabric of physics, they remain a beautiful idea waiting for a universe to prove them real. The very nature of reality might be an illusion, a cosmic sleight of hand. The 34th secret is the holographic principle, a radical idea born from the struggle to understand black holes. It suggests that all the information describing everything within a three-dimensional volume, every star, every atom, even your own consciousness, is not stored within that space at all. Instead, it is encoded on the two-dimensional surface that surrounds it like a hologram. For a black hole, this surface is its event horizon. The three-dimensional reality of everything that falls in is painted in a scrambled and fundamental way onto the two-dimensional boundary of the black hole itself. Our universe, in its most fundamental description, might not be the rich three-dimensional expanse we perceive. It could be a holographic projection from a distant, two-dimensional surface, with the event horizon of a black hole giving us the clearest hint of this profound truth. This leads directly to a parallel idea: black hole complementarity. This principle tackles the information paradox by proposing a strange kind of cosmic relativity. It states that two contradictory stories can both be true depending on your point of view. From the perspective of an astronaut falling into a black hole, they cross the event horizon smoothly and uneventfully, eventually meeting their fate at the singularity. But for an outside observer watching this happen, the astronaut never actually crosses the horizon. Their information is smeared and hotly encoded onto the event horizon's surface, where it radiates away as Hawking radiation. Both perspectives are correct within their own reference frames. The universe, in its deepest workings, does not have a single, objective truth about what happens at the precipice. Information is not destroyed. It is either inside or on the surface, but never both from the same point of view. These are not just abstract puzzles for physicists. They are clues that space and time themselves may be emergent properties, not fundamental building blocks arising from a deeper, more complex network of information. The event horizon is not just a boundary in space, but a frontier in our understanding, forcing us to question the very nature of existence. The profound warping of spacetime around a black hole opens a door to one of the most dizzying possibilities in all of physics. The 36th secret is that a spinning black hole could, in theory, function as a time machine. This is not science fiction fantasy, but a direct consequence of Einstein's equations taken to their logical extreme. Within the ergosphere of a rotating Kerr black hole, where spacetime itself is being dragged at near light speed, the distinction between space and time becomes blurred. Here, the mathematics allows for the existence of closed time-like curves, paths through the cosmos that loop back onto themselves. An object or person traveling along such a curve would find their future pointing directly into their own past, creating a loop in time. It is as if the twisting of spacetime by the black hole's immense spin stitches the fabric of reality into a Möbius strip, where the end of a journey is also its beginning. This theoretical pathway immediately confronts the infamous grandfather paradox. If you were to travel back in time and prevent your own grandfather from meeting your grandmother, you would create a logical contradiction that erases your own existence, making the journey impossible in the first place. The universe seems to abhor such contradictions, and a potential solution comes from the Novikov self-consistency principle. This idea proposes that the laws of physics simply will not allow paradoxes to happen. Any action you take in the past was always a part of that past, woven seamlessly into the timeline. Your attempt to change history would be thwarted by an infinite series of unlikely coincidences, a conspiracy of small events ensuring you fail. The gun would jam, a sudden noise would distract you, or your own hesitation would intervene. You were always there, and your actions always led to the present you know. The black hole, a destroyer of matter, might paradoxically be a guardian of causality, its extreme physics enforcing a single, unchangeable history. Even the most voracious cosmic giants face a natural limit. There is a secret cap on their growth, a point where their own power becomes their greatest obstacle. This is the AGN blowout, a self-imposed cosmic diet that prevents a black hole from gorging without end. As a black hole feeds and its accretion disk blazes with the light of a quasar, it does more than just shine. It unleashes a torrent of radiation so intense that it physically pushes against the very gas clouds that are its food. This outward pressure of light battles the inward pull of gravity. For a time, gravity wins, pulling more material in. But as the black hole grows more massive and its feast becomes more furious, the radiation pressure grows exponentially. Eventually, it reaches a point of equilibrium, a standoff where the outward push of light perfectly balances the inward pull of gravity. This is the Eddington limit, the maximum brightness a black hole can sustain. If it tries to feed faster, the resulting radiation becomes so powerful that it blows the surrounding gas and dust clear away like a hurricane scattering leaves. The black hole's own brilliance slams the pantry door shut, cutting off its fuel supply and forcing it into a period of quiet fasting. Its growth is stalled by its own cosmic feedback. Beyond this self-regulating mechanism lies an even more fundamental boundary, a cosmological limit set by the universe itself. There is only a finite amount of mass available in the observable cosmos. Even if a black hole could devour every star in every galaxy and all the intergalactic gas, there is simply a maximum amount of stuff it could ever consume. Furthermore, the universe is expanding, accelerating the flight of galaxies away from one another. Over trillions of years, the cosmic buffet will become increasingly sparse, with most matter receding beyond the black hole's gravitational reach. The combination of its own self-limiting outbursts and the ultimate scarcity of the cosmos means that no black hole can grow indefinitely. There is a final, absolute number for its mass, a point where it has consumed all it ever will, destined to drift in an ever-darkening void as a silent, sleeping leviathan. The vast cosmic web of galaxies did not assemble by chance. On the grandest scale, the universe is a tapestry of immense filaments and cavernous voids, a structure that might owe its existence to the most powerful engines within it. The 38th secret asks whether supermassive black holes were the architects of this cosmic lattice. Their influence appears to extend far beyond their home galaxies, shaping the distribution of matter across billions of light years. When a black hole enters its quasar phase, its outpouring of energy is so colossal that it can heat the intergalactic medium for millions of light years around it. This process, known as feedback, does not just regulate star formation within a single galaxy. It can prevent entire clusters of galaxies from cooling down and forming new stars, effectively putting a cap on their growth. The relativistic jets from active black holes pump energy into the spaces between galaxies, carving out vast bubbles and influencing where new gas can condense to form future galactic structures. In the early universe, these outbursts could have acted like cosmic landscaping tools, sculpting the primordial gas into the web-like pattern we observe today. They helped create the voids by pushing matter aside and seeded the dense filaments by triggering collapses in other regions. This speculative role positions black holes not as mere inhabitants of the cosmos, but as fundamental shapers of its very architecture. Their violent, energetic youth may have written the blueprint for everything we see, from the largest cluster to the smallest dwarf galaxy, weaving the dark and luminous matter into a single, coherent structure. The hunt for the cosmic missing link continues within the ancient stellar cities known as globular clusters. These dense balls of stars orbiting our galaxy like cosmic bees may be hiding intermediate mass black holes. These are the elusive middleweights with masses ranging from a few hundred to a few 100,000 suns. They are the crucial stepping stones between the black holes formed from single stars and the supermassive giants at galactic centers. Finding them would complete our picture of hierarchical growth, showing how the titans could have grown from smaller seeds through a series of mergers. Yet their detection is incredibly difficult as they often lurk in quiet states, their gravity only subtly influencing the motions of the surrounding stars. Another promising hunting ground is within small, faint dwarf galaxies. These relics from the early universe may still host the original, seed black holes that never grew into supermassive giants, offering a pristine window into the first generation of these objects. A different and brilliant method for this search relies on nature's most precise timekeepers, millisecond pulsars. These are the rapidly spinning cores of dead stars, emitting beams of radio waves with the regularity of an atomic clock. Their pulses are so predictable that any tiny glitch, any minuscule shift in timing, is a glaring signal that something is wrong. astronomers realized that an unseen intermediate mass black hole passing near such a pulsar would exert a faint gravitational tug, causing its pulses to arrive at Earth just a fraction of a second early or late. By monitoring networks of these cosmic lighthouses, scientists can effectively use the entire galaxy as a gravitational wave detector, listening for the silent footsteps of invisible black holes wandering through the dark. Each rhythmic pulse is a potential alarm bell, signaling the presence of a hidden giant drifting between the stars. There is a strange and beautiful symmetry hidden in the cosmos. The same dark giants that pull matter together with their immense gravity might also be fueling the very force that tears the universe apart. This is the deeply speculative 41st secret, a potential bridge between black holes and dark energy. We have long known that the expansion of our universe is accelerating, driven by a mysterious repulsive force we call dark energy. The simplest explanation for this force is the cosmological constant, a kind of innate energy woven into the empty vacuum of space itself. But where does this energy come from? Some physicists now propose a radical answer. The interior of every black hole, from the smallest stellar remnant to the supermassive titan at a galaxy's core, could be a reservoir of vacuum energy. According to certain solutions in general relativity, the extreme conditions inside a black hole could generate a powerful repulsive force, a kind of anti-gravity, that acts to push the universe outward from within its darkest hearts. In this view, black holes are not just consumers of space but creators of it. Their collective interior energy could be the source of the cosmological constant itself, making them integral players in the cosmos's ultimate fate. The universe's acceleration would not be a feature of empty space but a direct consequence of these dark engines. Every galaxy with its central black hole becomes a fountain of cosmic repulsion, its inward pull balanced by an outward push from its very core. This idea remains highly theoretical, a whisper at the edge of our understanding, yet it offers a profound and elegant connection. The same objects that govern the life and death of galaxies could also be writing the final chapter for the entire universe, a final, hidden secret held in the void. Even the mightiest cosmic giants are not immortal. Their reign, measured in trillions upon trillions of years, will eventually come to a slow and quiet end. This final destiny is written in the quantum whisper of Hawking radiation. For nearly all of its life, a supermassive black hole is a net gainer of mass, absorbing more energy from the cosmic microwave background than it loses through this faint evaporation. But in the far, far future, when the universe has expanded and cooled to near absolute zero, that balance will shift. The great fast will begin. The black hole will start to lose mass slowly at first, in a trickle of particles so faint it is undetectable. Yet this process has a strange and powerful feedback loop. As the black hole loses mass, its event horizon shrinks. A smaller event horizon means a stronger gravitational gradient at its surface, which in turn increases the rate of Hawking radiation. The evaporation feeds upon itself, accelerating as the black hole grows ever smaller and hotter. What began as a barely perceptible leak becomes a steady stream, then a torrent. In its final moments, a black hole with the mass of a mountain will be blazing with the temperature of a star, its radiation pouring out across the spectrum. The end itself is not a silent fade. It is a final, violent burst, a flash of high-energy particles and gamma rays that signals the monster's complete dissolution. Where once a gravitational titan ruled, there will remain only a diffuse, fading cloud of Hawking radiation, spreading silently into the cooling darkness. All the mass it once contained, all the stars and worlds it consumed, is returned to the universe as energy, a final transformation in a life cycle spanning timescales beyond human comprehension. This ultimate fate raises a haunting final question. If every black hole is destined to evaporate, what legacy do they leave behind in a cold, empty cosmos? That slow evaporation of a black hole unfolds across almost unimaginable eons, a timescale so vast it challenges our very concept of reality. This leads to a secret so strange it borders on philosophy, the Boltzmann brain paradox. In a universe destined for eternal expansion and ultimate cold, the laws of probability take on a bizarre new meaning. Given an infinite amount of time, random quantum fluctuations in the void could, in theory, assemble almost anything. A single, fully formed rose might spontaneously appear, a marble statue could flicker into existence, or, in the most mind-bending possibility of all, a self-aware brain, complete with a lifetime of fabricated memories, could simply pop out of the emptiness. This brain would believe itself to be a person living in a real world, but its entire reality would be a fleeting accident, a momentary glitch in a dead cosmos. The probability of this happening is astronomically low, so low it is effectively zero for all practical purposes. But over the truly infinite timelines we are now considering, even events with odds of 1 in a trillion to the power of a trillion become not just possible but inevitable. And this is where the supermassive black hole re-enters the story. The spacetime surrounding an evaporating black hole is not a perfect vacuum. It is a seething quantum soup filled with the Hawking radiation that is slowly dismantling the giant. This environment, persisting for trillions upon trillions of years, becomes one of the most likely places in the entire future universe for such a random, conscious fluctuation to occur. The paradox cuts to the heart of science itself. We trust our observations to tell us about a real external world. But if disembodied brains with false memories are statistically more common than ordered structures like galaxies and planets in the far future, then what does that say about our own consciousness? How can we be sure that we are not just such a fluctuation, a brief, impossible thought in an endless dark? The black hole, in its dying whispers, forces us to confront the nature of our own existence and the ultimate reliability of the cosmos we think we know. This chaotic hologram on the event horizon is a cosmic scrambler of unimaginable complexity. When quantum information falls toward a black hole, it does not simply vanish into the darkness. According to our best current theories, the data that defined a star, a planet, or a person is not lost. Instead, it is chaotically redistributed and encoded across the entire two-dimensional surface of the event horizon. Every single bit of information, every quantum state, is broken down and spread across this boundary in an incredibly complex, non-local pattern. It is the universe's ultimate encryption device, taking the rich, three-dimensional reality of an object and translating it into a scrambled, two-dimensional code. An outside observer could, in principle, reconstruct what fell in by collecting and decoding every single piece of this holographic data. But the task would be so astronomically complex it is practically impossible. This scrambling preserves the information, but it happens at a frantic quantum pace. This frantic process leads directly to a radical and controversial idea, the firewall paradox. If information is being so violently scrambled and encoded onto the event horizon, what would an astronaut actually experience while crossing it? Einstein's theory of general relativity gives a very clear and gentle answer. The equivalence principle states that someone in freefall should feel nothing special at the event horizon. It would be a smooth, uneventful passage, a point of no return you would not even feel. But quantum mechanics seems to demand something far more violent. To scramble the information so quickly and efficiently, the horizon might need to be a place of immense energy. The firewall hypothesis proposes that the event horizon is not a peaceful, empty space, but a literal wall of searing high-energy particles. Any object crossing it would be instantly incinerated into a fundamental soup of particles. This firewall would preserve the quantum information by destroying the infalling object before its information could be lost inside, but it completely shatters the cornerstone principle of general relativity. You cannot have both a smooth spacetime and a fiery death wall. This is not a minor disagreement. It is a fundamental clash between our two most successful descriptions of reality, a screaming paradox that tells us our understanding of gravity and quantum mechanics is still profoundly incomplete. The event horizon is not just a boundary in space, but the front line in a battle for the soul of physics itself. This conflict between a smooth horizon and a fiery wall was sharpened into a devastating logical trap now known as the Amps paradox. Named for the physicists who framed it, this thought experiment forces a brutal choice between three pillars of modern physics, and we can only keep two. The first pillar is unitarity, the sacred quantum law that information can never be destroyed. The second is locality, the principle that things interact only with their immediate neighbors, not through mysterious action at a distance. The third is the equivalence principle, Einstein's elegant idea that an astronaut in freefall should feel nothing special when crossing the event horizon. The Amps argument proves with chilling clarity that you cannot have all three at once. If information is preserved and locality holds, then the event horizon must be a searing firewall. To save the astronaut's peaceful passage and the purity of Einstein's gravity, you must sacrifice either the immortality of information or the local nature of reality. Every option seems to demand a revolution in our thinking. Perhaps information is not lost, but it becomes hopelessly non-local, spread like a ghost across the universe in a way that violates our standard notions of cause and effect. Or maybe the equivalence principle is only an approximation, a gentle lie that breaks down completely at the quantum precipice. This paradox is not a mere philosophical debate. It is a screaming signal that our understanding of spacetime itself is flawed, that it must be woven from something more fundamental. The smooth, continuous fabric of general relativity cannot coexist with the frantic, discrete rules of the quantum world. The Amps paradox is the clearest signpost we have, pointing directly toward the final secret, a theory of quantum gravity that will rewrite the rules of reality. This elegant idea, known as ER equals EPR, proposes a breathtaking connection between two of physics' strangest phenomena. On one side is EPR, the famous Einstein-Podolsky-Rosen paradox, which describes quantum entanglement, that ghostly link where two particles can instantaneously influence each other no matter how far apart they are. On the other side is ER, the Einstein-Rosen bridge, which is the formal name for a wormhole. This conjecture boldly states that these two ideas are not just similar, they are two different descriptions of the exact same thing. Every pair of entangled particles, from those in a lab on Earth to ones separated by billions of light years, might be connected by a microscopic wormhole, a tiny bridge in the fabric of spacetime. It suggests that what we perceive as a mysterious, non-local quantum connection is actually a geometric tunnel, a physical structure so tiny it is hidden from our view. This transforms entanglement from a spooky abstraction into a tangible, physical link woven into the universe's very architecture. If this is true, then the fabric of spacetime itself might be built from a vast, cosmic web of quantum entanglement. Think of an unimaginably complex tapestry where each thread is a quantum connection, and the entire pattern woven together is the three-dimensional reality we experience. Space is not a fundamental background. It emerges from these deeper quantum relationships. And where do we find the most intense, complex entanglement in the universe? At the event horizons of black holes. This makes black holes the ultimate testing ground and the key players in this cosmic scheme. The information that falls into a black hole is not lost precisely because it remains entangled with the radiation leaving the horizon, and this entanglement could be physically represented by a wormhole link. The black hole is not a lonely grave, but one end of a bridge to somewhere else, its interior potentially connected to the outside universe through a labyrinth of these quantum tunnels. This single, elegant equation, ER equals EPR, offers a potential path to resolving the great paradoxes, painting a picture of a universe where the largest structures and the smallest particles are intimately, physically connected in a way we are only beginning to comprehend. That ultimate scrambling of information at the event horizon might not be chaos but a calculation. The 48th secret reimagines a black hole as the universe's most powerful quantum computer. Every single particle that falls in carries with it a quantum bit of information, a qubit. The two-dimensional surface of the event horizon acts as a vast dynamic memory register, storing these qubits in a constantly changing state. As new information arrives, it interacts with the data already imprinted there, and the black hole's own internal dynamics perform a staggering computation. This is not a calculation in the sense of running a software program. It is a fundamental physical process, a transformation of quantum states governed by the laws of gravity and quantum mechanics. The black hole is processing reality itself, translating the three-dimensional complexity of stars and gas into a two-dimensional holographic code. This perspective gives us a completely new language for understanding the information paradox. The question of where information goes is turned on its head. It does not go anywhere, it is being processed. The black hole is not a shredder, but a cosmic CPU, and the Hawking radiation it slowly emits is not random noise, but the output of that computation. It is the result of the processed information leaking back into the universe in a form that is, for now, almost impossibly complex for us to decode. This reframing suggests that spacetime itself might be an emergent property of such quantum computations, a visible manifestation of information being processed at the most fundamental level. The universe we perceive could be the result of a cosmic calculation happening at the edge of darkness. Our existence itself might be a silent testament to the black hole's cosmic necessity. This is the 49th secret, a connection to the anthropic principle. This philosophical idea suggests a startling possibility that the fundamental laws and constants of our universe appear fine-tuned for one specific outcome, the emergence of conscious life. Why is gravity the exact strength it is? Why do protons and electrons have their precise charges? If any of these values were even slightly different, galaxies could never have formed, stars would not shine, and life would be impossible. Now consider the role of the supermassive black hole. Its specific properties are not arbitrary. Its mass, its stability, its very presence at the galactic center, all of these were crucial for building a universe that could eventually ask questions about itself. Without these gravitational anchors, galaxies might have remained formless clouds of gas, never achieving the stable, rotating structures that allow for orderly solar systems to form. A universe without supermassive black holes would likely be a universe without galaxies, and therefore without stars, planets, or people. Their feedback mechanisms, which we explored earlier, prevented galaxies from consuming all their gas in a single, frantic burst of star formation, allowing for long-lived, stable stellar populations like our Sun. They helped create the cosmic environment where life could slowly and patiently evolve over billions of years. This places the black hole in an eerie new light. It is not just a destructive monster or a galactic regulator. It is a key component in a cosmic recipe so precise that its slightest alteration would have rendered the universe barren. We can only observe a universe with black holes because in a universe without them, there would be no one here to observe anything at all. This final secret gathers all the threads, asking if the ultimate purpose of a supermassive black hole is to be a gateway. We have seen how they twist spacetime into knots, how their singularities might be bridges rather than endings, and how quantum entanglement could weave them into a cosmic network. The most speculative yet compelling vision from a future theory of quantum gravity is that these giants are not tombs but terminals. Under conditions we cannot yet engineer or even fully describe, a black hole could be a stable portal, a cosmic transit point. It might connect to a different epoch in our own universe, a distant galaxy, or a separate reality with entirely different physical laws. This is not a journey for matter as we know it, which will be torn apart, but perhaps for quantum information itself, the fundamental data of existence, transmitted through the spacetime tunnels hinted at by the mathematics. There is not a shred of observational evidence for this, and it remains a playground for theoretical physicists. Yet the mere possibility forces a profound shift in perspective. These dark giants, which we first saw as the ultimate end, compel us to ask if they are also a beginning. They are the universe's most extreme challenge to our understanding, pushing us to wonder not just what they are, but where they might lead. The greatest secret they hold may be that the boundaries of reality are far more porous and far more mysterious than we ever dared to dream. This final confrontation with the unknown reshapes our very definition of reality. For centuries, we have trusted that through observation and reason, we could uncover every secret of the cosmos. Supermassive black holes stand as a monumental challenge to that belief, forcing us to ask if some truths are fundamentally beyond our reach. They exist as tangible objects, their gravity felt across millions of light years, yet their deepest interiors are places where our laws of physics dissolve into pure mathematics. We can describe a singularity with elegant equations, but we can never observe it. We can theorize about the fate of information, but we may never know for certain if it is preserved or lost forever. This is a humbling frontier, a permanent shadow on the map of knowledge. It suggests that the universe contains realms that will always belong to the domain of thought, not empirical proof. The existence of these limits is not a failure of science, but a profound philosophical revelation. It teaches us that the cosmos is vaster and stranger than our tools can ever fully capture, and that the ultimate purpose of these dark giants may be to remind us of the beautiful, eternal mystery at the heart of everything. Our journey through these 50 secrets reveals a story far grander than simple destruction. We have traced the violent birth of these giants from primordial seeds, watched them feast in brilliant quasars, and seen how their powerful feedback sculpts galaxies, imposing order on a cosmic scale. They are not monsters, but master architects, their gravity the invisible hand guiding the evolution of the stellar cities they call home. Their very existence challenges our understanding of reality, from the information paradox at their horizons to the potential for wormholes and quantum connections at their cores. To study them is to probe the most fundamental laws of physics, where gravity and quantum mechanics collide. The silent presence of Sagittarius, a star at the heart of our Milky Way, is a constant reminder of this cosmic drama. The next time you look up at the night sky, remember the invisible engine spinning in the darkness, a testament to the universe's beautiful and terrifying complexity. Its greatest secrets are still waiting, hidden in the dark, for the next curious mind to